Hello, fellow Acme Drawing Corp employees. Today we are here to discuss the recent manufacturing issues with our steel mixing bowls. Normally, we use ASTM A36 steel, but due to the global pandemic, there has been a major shortage of this material. It was determined that AISI 1018 steel is a suitable alternative since it has the ultimate tensile strength and elongation properties required for our mixing bowls. To avoid another shortage, we purchased a multi-year supply of this steel. Unfortunately, when doing a test run on the factory floor, the normally smooth finish of our mixing bowls was found to be very rough, and this would greatly impact the quality of our products. Nobody likes a sticky mixing bowl. After running some mechanical tests, it was found that AISI 1018 steel undergoes discontinuous yielding when it starts to deform. This results in the rough surface finish of our mixing bowls. Discontinuous yielding is a phenomenon found in steel that occurs in two parts. The first part, the upper yield point, occurs when dislocations or holes in the crystal structure break free from the carbon atoms that pin them in place. The dislocations multiply and diffuse throughout the material as more strain is applied. The second yield point occurs when the dislocations are evenly distributed throughout the material. After this point, the dislocations are pinned in place again and continuous yielding occurs.
In order to suppress the yield point of AISI 1018 steel, there were two methods that we used with the available equipment provided, a roller and a furnace. It was decided that the steel would be cold worked and then heat tempered afterwards. This was based on the idea of temper rolling, which is a known finishing process in industry. We decided to have two variables for our experiment, the amount of cold working and the effect of tempering temperature. Cold working is the process of working/rolling the metal at a temperature below recrystallization temperature, or better known as room temperature, by plastically deforming it. It is often expressed as a percentage to show the degree of plastic deformation, where A0 is the original cross-sectional area and AD is the cross-sectional area after deformation. This can be seen as the equation on your screen right now. Tempering is the process of heat treating a metal after said hardening at a temperature below the critical point. To demonstrate the effect of cold working, samples A and B were cold worked by different amounts. Sample A was 20% cold worked, while sample B was 30% cold worked. Both of these samples were then tempered at 150 degrees Celsius. In order to test the effect of tempering, sample C was cold worked the same amount as sample A, but was heated at 200 degrees Celsius instead. Time in the furnace was kept constant for 1 hour. Finally, an Instron 1018 was used to record the displacement and force used during the tension testing, and this data was used to create a stress-strain graph. We thought that any cold working and tempering the steel would lower the yield point and eliminate any discontinuous yielding, which is the cause of the rough surface finish. The cold rolling would shift dislocations in the steel and potentially eliminate some of them. Afterwards, tempering in the steel will allow for diffusion of the interstitial carbon and dislocations, which would help in removing discontinuous yielding.
The stress strain diagrams of all three samples in the original sample of AISI 1018 steel were generated to interpret how the cold rolling and tempering had affected the steel. These diagrams show how a material will deform when a load is applied and will give us data on a material's properties. The yield point and ductility will be examined in these stress strain diagrams. The yield point is where plastic or permanent deformation of the sample starts, and the ductility shows how much the sample can be deformed before it breaks or fails. For all the samples, the treatments were successful in suppressing the yield point to stop the discontinuous yielding that had occurred in the original samples. If there had been discontinuous yielding, then there would be a serrated line like in the original sample. So the cold working and tempering had reduced the number of dislocations to suppress the discontinuous yielding, but there was also a change in ductility in comparison to the original sample. In sample A, the yield point was approximately 500 megapascals, and the ductility was approximately 7.8%. In sample B, the yield point was approximately 550 megapascals and had a ductility of just over 6%. Finally, sample C had a yield point of 525 megapascals and a ductility of just over 8%. In comparison, the as-received sample had a yield point of around 375 megapascals and a ductility around 30%. So while the cold working and tempering had eliminated the discontinuous yielding, it also decreased the ductility of the steel substantially and increased the yield point. So our treatments were successful in eliminating the secondary yield point to stop discontinuous yielding. It also slightly increased the yield point of the samples, and unfortunately the process had a detrimental effect on the ductility of the samples in comparison to the ductility of the original.
We would recommend Sample A's processing technique to be applied to our current processes to address the issues we are currently facing in our manufacturing process. Of the 3 samples that we treated, applying 20% cold work to the sample, followed by tempering the sample at 150 degrees Celsius for 1 hour, achieved the most desirable properties of the 3 samples. This is a preliminary study, and more research should be done into the tempering of the steel, as all samples were tempered for 1 hour. The benefits of using Sample A's technique is that it uses the least amount of cold work and heat of our 3 samples. As such, from an economical standpoint, this processing technique is the most favorable, and it also eliminates the secondary yield point. More testing should be done, since in eliminating the secondary yield point, the ductility was reduced. All samples were tempered for 1 hour, so testing could be done to explore the effect of tempering time on the ductility of the steel. The lack of ductility could create issues during the forming process of our products. Despite this, the readily available nature of AISI 1018 steel and the processing that it can be done using Sample A as an example makes this a more attractive proposition than sourcing ASTM A36 steel, as long as the decreased ductility is not an issue.